Hello, this is Thavamani Govindaraj from Tampere University. The title of my today's talk is Saturated Output Regulation of Distributed Parameter Systems with Collocated Actuators and Sensors. This is a joint work with Dr. Yokohama Humalaya and Professor Lassi Paunanan. This is the outline of my talk. I will start with the main problem and then I will talk about the results. And then I will present an example to illustrate our results. So let's start with the main problem. In reality, it is natural to consider limitations in the actuators. This is called input saturation. Taking actuator limitations into account, linear systems subject to input saturation has the form given by these equations. Here pi is a saturation function where the input u of t takes values in a certain closed interval. In this work, we focus on output regulation of infinite dimensional linear systems subject to input saturation. In particular, we consider class of abstract linear systems of the form given by these equations on a real Hilbert space X. Here x of t is the state variable, u of t is the input, y of t is the output, w of t is an external disturbance, and pi is a saturation function. The saturation function pi is defined as follows. The considered class of systems arise in the study of systems with collocated actuators and sensors. Our goal is to find a linear feedback control law, u of t, such that the output of the system tracks given reference signal asymptotically. We extend the output regulation theory in the work by Sabari and their co-authors for finite dimensional systems subject to input saturation to the considered class of systems. The reference signals to be tracked and the disturbance signals to be rejected or assumed to be generated by an exosystem of the form given by these equations on a finite dimensional space W. Here, S, F, and E are matrices of suitable sizes. We make the following assumptions. The operator A generates a C0 semigroup of contractions on X. B is a bounded linear operator from the input space to the state space X, and the operator A minus kappa B star generates a strongly stable contraction semigroup for any kappa greater than 0. The spectrum of S lies on the imaginary axis. From the output regulation theory for finite dimensional systems subject to input saturation, we know that the output regulation problem is not solvable for all initial conditions of the exosystem, meaning that there exists at least one initial condition of the exosystem for which the tracking is not achieved. In this work, we focus on semi-global output regulation problem where the initial conditions of the exosystem are restricted to a compact set. So the semi-global output regulation problem considered in this work is defined as follows. Consider a compact set W0. Our goal is to find a linear output feedback control law in the form given by these equations, such that kappa greater than 0, L belongs to L is a vector of size 1 by Q, and the origin of the system given by these equations is globally asymptotically stable for all initial conditions of the system, the initial conditions of the exosystem in the compact set W0, the error between the output y of t and the reference signal decays to 0 asymptotically. Next, let us discuss our results, which give solvability conditions and the control law for the semi-global output regulation problem. Our main result is an infinite dimensional generalization of the work by Sabari et al. Our approach for showing the asymptotic convergence of the regulation error is motivated by the techniques in curtain and spot. This is our main theorem. Consider the compact set W0, which is a subset of a finite dimensional space R to the power Q. Under the given assumption, the semi-global output regulation problem is solvable if there exist phi and gamma given as here, such that they solve the regulatory equations given by these equations, and there exists delta greater than 0 such that supremum norm of gamma v of t is less than or equal to 1 minus delta for all v of t with v0 belongs to w0. In this case, for any kappa greater than 0, the feedback law given by this equation solves the semi-global output regulation problem. Here we give an outline of the proof. The first is we have to prove the origin of the system when disconnected from the exosystem is globally and asymptotically stable. So this can be done by using the strong stabilizability of the system by negative output feedback and uniform Lipschitz continuity of the saturation function and a result from curtain and spot. Next, we have to show the regulation error decays to 0 asymptotically. For that, we introduce a variable psi of t in terms of the states x of t and b of t, which is the mild solution of the system given by these equations. Now, by using the assumptions of the theorem, we can show that the mild solution psi of t decays to 0 asymptotically. So this will imply that the regulation error can be written in this form. This term equal to 0 from the regulatory equations. And we have already shown that psi of t converges to 0 asymptotically. So therefore, the whole term y of t minus y of t converges to 0 asymptotically. Here we present a lemma which gives solvability conditions for the regulatory equations. Let A minus kappa BB star generate a strongly stable contraction semigroup for any kappa greater than 0. Assume that the spectrum of X lie on the imaginary axis and S has no non-trivial Jordan blocks. Then the regulatory equations are solvable if and only if no eigenvalue of S coincides with a transmission 0 of the system ABB star. In this case, phi and gamma are given by these expressions, where I omega k and phi k are the eigenvalues and the corresponding orthonormal eigenvectors of S respectively, and G is the transfer function of the system ABB star. Next, I will present an example to illustrate our results. We consider a dynamic model of a flexible satellite composed of two symmetrical flexible solar panels and a center-rigid body. The equations of motion of this satellite model are described by these equations. Here U of t, y of t are the input and the outputs on the center-rigid body. We also consider a disturbance on the center-rigid body. the boundary conditions corresponding to the free ends of the beam and the coupling conditions between the solar panels and the central rigid body are given by these equations. The measured output is given by this. The satellite model can be written in the form, where the operator A generates an exponentially stable contraction semigroup on the Hilbert space X. It can be also verified that A minus kappa B B star generates an exponentially stable contraction semigroup on X for any kappa greater than 0. Our goal is to track the reference signal of this form and reject the disturbance of this form. It is a constant disturbance. Motivated by these signals, we choose the exosystem given by these equations. Here the eigenvalues of this matrix are given by 0 and plus or minus 1.5i. Moreover, the satellite system does not have any transmission zeros at these eigenvalues. This implies that the regulator equations are solvable, and the controller parameters can be obtained by using these expressions. And they are given by these terms, where G is the transfer function of the satellite system. We have run some simulations with kappa equal to 100. Here we can see the behavior of the saturation function and also gamma into V of t. We can see this is below the saturation level for all t greater than 0. And also output tracking is achieved using this control input asymptotically. It's time to conclude our talk. We considered class of strongly stabilizable infinite dimensional linear systems with collocated actuators and sensors subject to input saturation. We proposed a linear output feedback control law that solves the semi-global output regulation problem. The results are illustrated with an example of a flexible satellite model subject to input saturation. These are our references. Thank you.